Welcome back to my series on Calc 3. My name is Dr. Matthew Michael. Teach here at NJIT. We're going through the Thomas and Larson books, talking about Calculus 3, how to take derivatives and integrals and move them into multivariable space. Exciting. Last time we finished off talking about the first type of vector multiplication, the dot product, also known as the scalar product. I mentioned that there was a second one. This is it. The big one. The big kahuna. The one that confuses everybody. This is the cross product. Well, remember the right-hand rule? That's what this basically boils down to. I take the vector, which is my pointer. I take another vector, which is the rest of my fingers, my thumb. Well, let U be my finger. Let V be the rest of my fingers, and let my cross product be my thumb. The cross product is the mathematical equivalent of the right-hand rule. Logically, you could expect there's a lot of applications in your different fields. It's going to be orthogonal to both of these vectors. And like I mentioned before, it's called the cross product, or the vector product, because you get a vector out of it. So your cross product is your thumb coming out, just like I mentioned a few moments ago. And we talked about how to find that theta before between V and U from our dot product. So if I have U and V, if I can calculate it like so, U cross V is U2V3 minus U3V2 I minus U1 V3 minus U3V1 J plus U1 V2 minus U2 V1 K. Simple, right? No, not so much. So there's a lot of different ways of calculating it. In my opinion, the easiest way is what's known as the determinant. We have I, J, and K in the first row. We have the components of U and V in the second and third rows. The first term in the cross product goes in the second row. The second goes in the third row with the different unit vectors here on top. But how do I calculate this determinant? While it does come out as this lovely, disgusting formula, it's actually easier if you do it this way. This is out of the Larson textbook. So if I want to find the I component of my new vector, take a look at my I. My I will cross out everything else in the same row, in the same column, and it's going to take a look at this inner bit right here. And it's going to multiply that nice pretty value by my I. If I want to find the J component of my new vector, it's going to be negative of this. If my leftovers are U1, V1, U3, V3, and this right here. If I want the K component, I take what's left after I cross out everything in the same row and column as K. Notice there's a negative sign in front of the J. And then I do what's known as the determinant of the 2 by 2. How do I do this? We multiply across the diagonals, AD minus BC. So if I have the determinant of 2, 4, 3, negative 1, it's 2 times negative 1 minus 4 times 3. Or negative 2 minus 12, which is negative 14. Or the determinant of 4, 0, negative 6, 3 is 4 times 3 minus 2 times negative 6, or 12. So notice if I have U2 times V3 minus U3 times V2, U1 times V3 minus U3 minus times V1. So if you want to memorize this formula, kudos to you. I like writing it in this determinant form. You're going to need to choose which way works best for you. But if you are going to use this formula in my class, write down the formula before you use it. Something interesting pops out though. Because they are, notice these are on top of each other and we're canceling them out by cross-multiplying. If one vector is just a scalar multiple of the other, that means that that scalar will cancel out when I'm subtracting, which means the cross product of two parallel vectors is actually 0. So now we have two things we can do. We can check if they're perpendicular or parallel by both of the different types, by one of the different products of vectors. So if we're checking for whether the vectors are parallel, cross product. If we're checking for perpendicular, dot product. So let's actually compute a cross product. 1i minus 2j plus k, 1k, and v being 3i plus 1j minus 2k. So that means I'm going to have I, j, k on the top, 1, negative 2, 1, negative 2, 1, 3, 1, negative 2. There. Break it up into its different components. So cancel out everything in the same column and row. We get negative 2, 1, 1, negative 2. Plug everything in, calculate, and my new vector is 3i, 5j, 7k. For kicks and giggles, we can also calculate the cross product of v and u. Because we talked about last time that that dot products, it doesn't matter which order you do it in. So does the order matter? Why, yes, it does. If you flip the order, you flip the signs. So u cross v is the same thing as negative v cross u. And it makes sense because instead of crossing like so and coming out this way, I'm instead curling the opposite direction. That's why. These are all the different things, and while most of them are pretty straightforward, the one I really want to direct your eyes to is number 3. That's perhaps one of the harder ones. And number 6. It's number 6 does weird things. If you want to take a look at number 6, remember cross products are vectors in and of themselves, and so this weirdness comes in because of it. Some different geometric interpretation of what's going on. We already talked about how the cross product is like the right-hand rule, so it does make sense that the cross product can be orthogonal to both of our original vectors. Because of our original setup for this, the magnitude is going to be given as follows below. And notice number 2 is just this. So the length of this of my thumb vector is going to be given by the magnitudes of u and v times sine of theta. Remember, that's the angle between them. Remember I mentioned that magnitude can either use one set of absolute values or 2. We mentioned about parallel. Interesting number 4, that magnitude we calculated here, magnitudes of u and v sine theta, that's actually the parallelogram that we constructed using the dot product by addition of the addition of the two vectors. That parallelogram that shows up, you can calculate the area of that parallelogram with the magnitude of the cross product. Because of this. Height is going to be v sine theta. Then we need a length for a base, so base times height. That's why it works out the way it does. Pretty nifty. So triangles are half of a parallelogram, so half of the magnitude. Torque. You can find the magnitude of torque by, because remember the torque is just going to be, or maybe you don't know, is the cross product of the position that we rotated, r, and the force we use to turn the cross product here, r cross f. the magnitude of that gives us this. So we found area. Can we get volume out of it? Volume is just length times width times depth, or area times depth. We already know that how to calculate area. That's just cross product. So can we get depth out of it? Can we get volume out of this? Well, volume itself is a scalar quantity of its own. So how cross product turns two vectors into one vector, and we have to reduce that vector into a scalar quantity. So what do we have to multiply that vector by in order to get a scalar out of it? We need to do a dot product, or scalar product. So the volume of a shape, which we call the parallel pipette, is u cross v dotted with another vector, w. So u being one side, v being another side, and w being another. So that's our parallel pipette. Think of it as the quadrangle or the parallelogram in the three-dimensional space. How do we find it? Well, instead of having I, j, and k, just add an extra row. Replace that with your w. So when we calculate it out, I accidentally put two rows in there. We can do that, and we simplify it out, and we find that the parallel pipette that's given by u is equal to 2j minus 2k, that means 0i, plus 7 v is equal to 3i plus j plus k, and w being 3i minus 5j plus k. Those three vectors imply that if you take the area, the volume generated by these three vectors, you get a volume of 36. Alright. Hope this is helpful. If you have any questions, contact me down below.